In this video, we look at more questions about lines and planes, and I really like these questions. They're very simple questions for the most part, and they really get to the heart of whether or not you understand these formulas and what they mean. So we're going to answer them one at a time. We'll take time as necessary. So here we've got parametric equations of a line. And someone might ask you, I might ask you on a quiz, to determine whether the points given below lie on this line. Now remember what this equation, or these three equations mean. So we've got some line, it's in three-dimensional space. And at time t equals 0, we would be located at x equals -2 if I plug in 0. Actually, I'll call that x naught, y naught, z naught. When t equals 0, x is -2, y is 3 times 0, which is 0, and z is 4 plus 0, so 4. So we're here. And then as t increases, we trace out the whole line. So when t equals 1, we are at x equals -2 plus 1. Oops, that was t equals 0. This is t equals 1 in my little cartoon picture of my graph. At t equals 1, we're at location x equals -2 plus 1, which is -1. Y equals 3 times 1, which is 3. And z equals 4 plus 1, which is 5. And at t equals 2, we'd be over here. At t equals 3, we'd be over here. T equals -1, we'd be back there. So with all the values of t, as t takes on any real number, we get the whole line. So in general, this point is given by x of t, y of t, and z of t. So that's a location, and it's equal to -2 plus t for our x value, 3t for our y value, and 4 plus t for our z value. Those t's are all exactly the same. So when t equals k, we're going to be at location -2 plus k, 3 times k, and 4 plus k. Whatever t is, you just plug that in and that's going to give you the location. So this question says, is this point on this line? So how can we figure out whether this point lies on this line? I hope you're thinking, well, that's the x, that's the y, and that's the z. So I guess the question becomes, is there some t value so that x is 0 when y is 6 and z is 6? So to figure that out, we're just going to set up a system of equations. This is the x, that's the y, that's the z. So we want -2 plus t to be 0, and 3 times t to be 6, and 4 plus t to be 6. So that's my x, that's my y, that's my z. And we want all three of those to be satisfied at the same time. Now, if this one's 0 when t equals 3 and the other one's 0 when t equals 4, it doesn't help us. That means that point's not on our line. These all have to be 0 at the same time. So I'll solve this top equation for t. Get t equals 2. If I substitute t equals 2 into here, do I get 6? Yes, that checks out. If I substitute t equals 2 in here, do I get 6? 4 plus 2 is 6. Yes, that checks out. So yes, this point is on the line. Yes. If we're thinking of t as representing time, and this being the trajectory of some object that's just traveling along the line at a constant rate, every 1 second it increases, or it moves like this far. It moves the length of v along that line, where v is the direction vector. If I wanted to know the time that we were at this location, I'd say yes, this point is on the line, and that happens when t equals 2 seconds. Now when t equals 2, that wasn't asked. We were just asked to determine if that point lies on the line. But this is helpful if we're interpreting this as the position of some object at some point in time. Okay, so then the second question is, or same question, different point. Does this point lie on the line? We're going to do exactly the same thing. You set up a system of equations. You need the x value to be 2. So we need x to be 2, and x is negative 2 plus t. Y is 3, and that has to be 3 times t. And z is 5, and that has to be 4 plus t. Okay. If x, which is 2, is equal to negative 2 plus t, then t would have to be 4, right? If t equals 4, is 3 times 4 equal to 3? Is the second one satisfied? No. If t equals 1, this is satisfied, and if t equals 1, this is satisfied, but if t equals 1, this top one isn't satisfied. So these are not all satisfied at the same time. So we'll say the point 2, 3, 5 does not lie on our line. Okay. Now we have a geometry question. We're asked to find the points where the line intersects the xy plane, the xz plane, and the yz plane, respectively. And then if the line doesn't intersect the plane, we want to explain. Now, lines are difficult to draw in 3D, but I want to draw my x and y and z axes just to get a sense of dimension, just to remind myself what everything looks like. Okay. If I want to see where my line intersects the xy plane, remember the xy plane is down here, and it's also behind us. There's the negative x-axis, and there's the negative y-axis. The other part of the xy plane is over there, and there's where x and y are both negative, and here's where y is negative, but x is positive. But this is where x and y are both positive, and there's the rest of it. Okay, and it keeps going. It extends in all directions. Remember what the equation of the xy plane is. That's z equals 0. So to figure out where our line intersects this plane with equation z equals 0, we just set the z value here to be 0, and then we solve for t. So that's the first thing we do. Or if we're given the equation of the line in this form, we know that z equals 0, so we set, this is our x, that's our y of t, and that's our z of t. We're going to set z of t equal to 0 and solve for t. So we'll subtract 2 from both sides and solve for t. We get negative 2 over 5. Now we have not answered the question yet. They asked for the points where the line intersects the xy plane, not the time. But it turns out at this time, at t equals negative 2 over 5, at this value of t, z is going to equal 0. To find the point, I need to substitute this value of t into my x of t, y of t, and z of t. So our location is x of negative 2 over 5, y of negative 2 over 5, and z of negative 2 over 5. And it looks like from our parametric equations, x is negative 4 all the time, regardless of what t is. And y is 2 minus 3 times the negative 2 over 5. So we're going to get negative 3 times negative 2 over 5 is 6 over 5. 6 over 5 plus 2, that's 6 over 5 plus 10 over 5, so 16 over 5. And then by design, if I plug in negative 2 over 5 here, I get the 5's cancel and I get negative 2. Negative 2 plus 2 is 0. So this is the point, that's the location in the xy plane where our line, or that's the point in the xy plane where our line is crossing it. So at x equals -4 and y equals 16/5, so that's what, 3.2? Our line crosses the xy plane right there. Okay. Don't quite have enough space for the other planes, but we can do the same thing. I want to know, where does this cross the y or the xz plane? And remember, the xz plane is back here. And there's another part of it over here. And then there's a part of it below us, part of it below that. So it's this plane over here. If this is my floor where I'm standing, like that's the XZ plane. It's the wall to the left of me if I'm standing here looking at you. Remember, it's to my left. Remember, the equation of this plane was y equals 0, and all the planes parallel to it are y equals a constant. So to find the point of intersection between our given line and this plane, we set y equal to 0, solve for t, and once we have the t value, that's our time when our line is crossing this plane, then we can find the corresponding x and y value. So you set y equal to 0, so you're setting y of t equal to 0. And then solve for t. So t equals 2/3. And then that's not it, that's the time, it's not the point. We want the point of intersection. So I need to evaluate x at 2/3 and y at 2/3 and z at 2/3 in order to figure out where our line crosses that plane. Now x is always -4. For this particular line. When t equals 2/3, y is supposed to be 0, right? Let's check. If I put 2/3 in here, the 3's cancel, and I have 2 minus 2, I get 0. That's good. And if t equals 2/3 here, I have 2/3 times 5, which is 10/3, plus 2. 2 is 6 divided by 3. So I have 6/3 plus 10/3, which is 16/3. All right, that's our location. So we go -4 units in the x direction, 0 units in the y direction, and then 16/3. So that's 5 1/3 units in the z direction. So we go back 4 and then up 5 and a little bit more than that, 5 1/3. You draw a little box like this, and that is where our line crosses the XZ plane. So we've got a line, 2 points determine a line in 3D as well as 2D. So it looks like this. Last question, we said, where does it cross the XY plane? It crossed there. And it says, where does it cross the XZ plane? It crosses over there. Question, does it ever cross the YZ plane? Is it ever up here? Maybe you already know the answer. If you don't, you can watch this YouTube video at twice the speed or something like that, so you don't have to listen to me explain. The YZ plane is back here. Remember, and then here's the rest of the YZ plane. Here's part of the YZ plane when x is negative, or when y is negative. And we're going to have part of the YZ plane when y is positive and z is negative, and then y and z are both negative over here. And this x-axis, it's coming out at us. Okay? remember the equation of the YZ plane is x equals 0. Is x ever equal to 0 on this line? No, it's not. X is always equal to -4. So it turns out our line never crosses the x or the YZ plane. Because it lies in a parallel plane. And that plane is x equals -4. So just to get a sense of what's going on again, let's draw it. We do the best we can. We said that this crossed the xy plane. The point of intersection was -4, 16/5, and 0. It crossed the xz plane at -4, 0, 16/3, and then it doesn't cross the YZ plane. Okay. So I'm going to draw a lot of those boxes that we talked about in class. X is -4. So I'm going to go backwards 4 units on the x-axis. And y is 16/5, so that's 3 1/5, or 3.2. So there's 3, there's 4. 3.2 might be about there. I'm going to draw a line that's parallel to the y-axis, or do the best I can, and draw a line that's parallel to my x-axis. And that's supposed to be -4, 16/5, and 0. And then our line crosses the xz plane at x equals -4, y equals 0, and z equals 16/3. 16/3 is 5 1/3. So that's 5, and there's 6. So we want to go third again higher. And draw a line that's parallel to the z-axis, draw a line that's parallel to the x-axis, and there's that point. And our line, it's in this plane back here. It's in the plane formed by this little square. It's in this plane. And it looks like that. And there's a parallel plane right in front of it. The YZ plane, like that's up here. It looks like that. So it's like I've made a rectangular box. The YZ plane is up here. This is given by x equals 0. And the plane that this is on is this other plane, this red plane. It's parallel to this purple plane, and it really doesn't have hard boundaries like that. It continues in all directions. I'm just drawing that so we can get some sense of what's going on. That's the plane with equation x equals -4. So it never crosses this plane because it stays back here in this other plane that's parallel to it. Okay. So now let's do 2 more. We want to determine whether a point lies in a plane, and then determine whether a line lies in a plane. That's a fun one. Okay, so actually determining whether a point lies in a plane is very easy. So we're given a plane, and the question is, does this point, -7 to -1, lie in the plane? Well, if it does, this x, y, and z should satisfy that equation. So we'll just plug it in. Negative 7 plus 2 times y minus 4 times z. Question is that equal to 1? If it's equal to 1, then yes, it lies in the plane. If it's not equal to 1, it's not in the plane. So let's work it out. We get negative 7 plus 4 plus 4. Is that equal to 1? I hope you said yes. So that means that point lies in the plane. It lies in the particular plane that we were given. X plus 2y minus 4z equals 1. And obviously, if we plug in a different point and we don't get 1, then that point does not lie in the plane. Let's see if this one lies in the plane. So substitute in your x. So we have x is 5 plus 2 times y, which is 2, minus 4 times z, which is 2. Question is that equal to 1? That's 5 plus 4, that's 9. 9 minus 8, is that equal to 1? Yes. So that one also lies in the plane. How about the origin? Does the origin lie in this plane? If I plug in 0, 0, 0, do I get 1? No. So the origin does not lie in the plane. Okay. All right, now we're going to put lines and planes together and look at a question about whether a line lies in a plane. Okay, so we're given this. Here are your possibilities. Either you've got a plane like this, and the line intersects it at a point. So there's some point, some particular t value where that line intersects the plane, and it's going to be at that location. X of, I'm just going to call it t naught, y of t naught, z of t naught. So there's one possibility. The line may intersect the plane at a single point. Another possibility is that the line lies entirely in the plane. Doesn't matter what t is. That line's in the plane all the time. So, in this case, I'm going to write for all t. That's going to help us. And what's the third case? If you've got a line and a plane, and of course we're assuming we've got the whole thing, not just this little part of it that I'm graphing. Well, if this is my plane, there are lots of planes that are parallel to that. It's possible that our line is not in our plane and it never intersects our plane. The only way it would fail to intersect our plane is if the line itself lies in a parallel plane. So maybe this is our plane and this is a parallel plane. So we're looking at that parallel plane, and that's where the line is, and so that line never crosses our plane. Kind of like the line in that last example. When we looked at this, that line lies in the plane x equals -4. It never crosses the plane x equals 0. That's exactly what we're talking about here. So the line might lie in the plane for all t, it might intersect at a point, or it may never cross our plane because it lies in a parallel plane. Okay, so the question is, how do you figure it out? Which one is it? Okay, and the key to this is to remember that every point on this line corresponds to x of t, y of t, and z of t for a particular value of t. So if we're thinking of this as the trajectory of some object, some path that our object is traveling along, there's a certain time. You give me a time t equals 5, and I'm going to be at a specific location, x, y, and z. And at a different time, I'm going to be at a different location, and at a different time, I'm going to be in a different location. But if you give me a t, these parametric equations give me that location of the particle on the line, or give us a specific point on the line if you prefer not to think about movement and motion. So if I want to determine whether or not this line intersects this plane, all I have to do is replace that x, that y, and that z with x of t, y of t, and z of t. Now this is an equation. Now it involves t. The question is this true all the time? For all values of t, do I always get 12? If this is true for all values of t, if this side is always equal to 12, then our line lies in the plane for all t. Now if this is never true, if you simplify this and you get this equals 10, well then this line actually lies in the plane 2x minus 2y plus z equals 10, not 12. If we get an equation that's never true for any t, our line lies in the parallel plane, whatever that left-hand side simplifies to, like that's the appropriate right-hand side of the parallel plane that our line lies in. Now if this is true for one particular value of t, if you do the algebra and you eventually get t equals 5, or t equals 10, or t equals -3, well that's telling you there is one point in time when that line crosses that plane. And at that point in time, we've got a point of intersection. Now it doesn't tell you what the point of intersection is. If you want the point of intersection, you've got to plug that t in to your x of t, y of t, and z of t to get the location. But if you get a single value of t, that just means, yeah, these parametric equations for the line, they satisfy the equation of the plane, but only at one point in time. We want to know, does it satisfy it at one point in time? Does it satisfy this equation for a plane all the time, no matter what t is? Or does it never satisfy the equation of a plane because this reduces to some number that's not 12? Let's see which case we're in here. So in our example, we were given x of t, y of t, and z of t. We're told that x of t equals 1/2. All right. And y of t equals -3/2 minus t. So from right there. And z equals -1 plus 2t. Okay, let's see what we get. If we distribute, I have 2 times 1/2 is 1. -2 times -3/2 is +3. -2 times -t is +2t. Then I have -1 plus 2t equals 12. All right. So I've got a 1 and a -1. Those are gone. So on this side, this reduces to 4t plus 3 equals 12. Okay, so subtract 3 from both sides. And we get 9. Divide both sides by 4. We get t equals 9/4. So that's 2.25. So there is one time, one moment, when this line crosses this original plane. And that apparently happens when t equals 2.25. Now, this is not the point of intersection, but it does tell us what time it happens if we've got some object traveling along that line. So we'll say the line intersects the plane when, that's a time, t equals 2.25 at the location given by x of 2.25, y of 2.25, and z of 2.25. And I'm just going to draw another cartoon. Here's my plane. Here's my line. It's supposed to be straight. At t equals 2.25, we're right here. What's the location of that point? It's x of 2.25, y of 2.25, z of 2.25. And x was given to be 1/2. I'm just going to write it in decimal form, 0.5. Y was negative 1.5 minus t. And z was negative 1 plus 2t. So I have 0.5. Negative 1.5 minus 2.25 is negative 3.75. This is negative 1 plus 4.5, or 3.5. Alright, so it looks like our equation. Our equations tell us that this line intersects the plane at x equals 1/2, or x equals 1.5, y equals negative 3.75, and z equals 3.5. Now, if you went through all of this and everything canceled, so eventually all the t's were gone and you got 12 equals 12. 12 equals 12 all the time, we would know then that the line lies in the plane for all t. If all the t's canceled and then you got something that was never true, like the t's are gone and now you have 5 equals 12, never true, well then our line lies in another plane, and if this simplified to 5, it would lie in the plane 2x minus 2y plus z equals 5. Okay, and that's it for our additional questions about lines and planes and geometry and time.